Just a very quick introduction. The O2 Group is a bit of an expanding group in Queensland. It's a kind of a diversified business of engineering, ecology, and located in these places. So pretty good coverage of most of Queensland and a little bit internationally. So I'm talking about high efficiency sediment basins, which are a kind of a concept that's getting traction in the construction industry in southeast Queensland. But I just wanted to introduce, I suppose, an application or an innovation of that technology into reef catchments. This is what I'm going to be talking about, but I'll spend the whole 10 minutes going through that, so let's get into it. What is a high efficiency sediment basin? Well, it's a sediment basin as you typically know it, a holding pond of water off the catchment. But what it's doing is it's actually actively dosing that water, the influent stream, with a coagulant. Rather than relying on the normal process of sedimentation, it's recognising that the fine colloidal material, which has got the majority of the constituents that we're interested in treating in the reef catchments associated with it. It's basically adding a chemical coagulant to this process to speed it up. Speeds it up, but it also means the footprint or the amount of water you need to store and for how long can be smaller. So that's a critical thing in how it might gain traction or application in reef catchments. Fairly simple, water in one end. The dosing arrangement is either triggered by a flow meter or a rainfall sensor, so it can be done automatically without a person out there having to do it. And effectively it flows linearly through the system in a fairly quiescent sort of low flow condition so that the flock falls out and the water is decanted reasonably clean at the back end. This is what one looks like in a fairly large construction site in southeast Queensland. We're looking from the top end to the outlet end with flow sensor instrument there. This is a quarry application in southeast Queensland looking from the decant end up to the top end. You'll see these are fairly large, very engineered systems because these are long-term applications. But it can be a very simple, quite agricultural application like this, where it's a small construction site in a rural setting, a simple constructed holding water pit, and a very simple dosing arrangement, which I'll talk about in a minute. Dosing is obviously an important part of how these work and I guess how simplistically they can be operated. Just go back to this one. The little green box there that you can see is called a flock box. I suppose an innovation out of New Zealand, like many things, but you know, beautifully simple. Beautifully simple. It basically measures rainfall onto it and uses basically a displacement mechanism to discharge coagulant into the influent water. Nice and simple from an operational point of view. Much more sophisticated systems, however, can use flow-based sensors and effectively use that as the mechanism to control the dosing rate of your coagulant into the influent stream to get accurate dosing for the quantity of water coming in. And there's a bit of back-end testing that sort of happens of the soil and water on the site that precedes this so that you can calibrate these kind of instruments. It's important that that gets done properly so that the systems function efficiently and you don't have troublesome residuals coming out the bottom end. The coagulant the company that I work for uses is a aluminium chlorohydrate, which is used fairly extensively in the water treatment industry. It's what's termed a pre-hydrolyzed chemical. Its benefit, I guess, in its application is it changes the charge of the water a bit to basically help the negatively charged colloidals just coagulate and then flocculate out. But the pre-hydrolyzed characteristic means it doesn't drive down the pH of the dosed water significantly, as opposed to some other coagulants. Its optimal operating range from a pH point of view is between 5.5 and 8. So, you know, really low pH water may need to be pre-treated with a lime treatment or so on, but in a lot of agricultural contexts that would be done as a matter of course by the farmer. It's high basicities. As I mentioned, it doesn't drive the pH of the dosed water down, and it works at pretty low dosing rates compared to some other forms of coagulant. But it's a little bit more expensive, so when it comes out it's about cost neutral with other forms. Ensuring that it's been applied at the correct dosing rates and buffering those pH conditions means you should be able to overcome any concerns around toxicity levels in residual aluminium and so on that might leave the system. I was going to be a bit facetious here and suggest that one tub of Turbiclear could clean up Johnson. I'm not going to do that, so let's move on. How might this get applied into Great Barrier Reef catchments? I guess the technology, which is scalable and is using a chemical coagulant to reduce the footprint of the technology, is where I think its application is. It's typically located back into the paddock as opposed to down the system on a stream, and it's offline, scaled to the local climate and could even treat tailwater from an irrigation regime. I think its maximum capability is up to about 100 hectares, but I think in reef catchments it would work at much smaller scales than that. And only requiring about 1 hour hydraulic detention time by virtue of the chemical coagulant means it's a very rapid rate of removal of those troublesome colloidal particles. Now, what happens once they're removed, I think is going to be of interest to people, and I'll talk about that in a short while. That relatively small footprint, and we've been talking about percentage of catchments areas, and it's been a bit of a confusing topic throughout the day, but if applied to, if you imagine a paddock and maybe a fallow paddock disturbed, we're talking about an area of 2% of that contributing paddock or area of fallow land. Whereas wetlands, there's been a lot of discussion around this, but I think if it's applied at the paddock or local catchment scale, will be around 5 to 7% to be operating optimally at that point of diminishing return. So I think it's this small footprint and relatively simple nature of this that makes it applicable and potentially attractive to some key industries in reef catchments. And I'm thinking here sugar and banana. And I think they're the potential applications because they are intensive in terms of their need for land, for production, and therefore anything that takes a big footprint isn't going to be an easy sell into that marketplace. And in a sense, we're working with sediment basins here or enhanced form of them, so we're working very much within the BMP framework that those farmers are already operating under. So it's not new, it's just enhancing the efficiency of what they are or should be doing. Some suggested applications in reef catchments. I think these front-end dosing systems could be easily retrofit to existing on-farm infrastructure. So my experience, having done some training up in reef catchments with farmers a few years back, is a number of them do have sediment basins on their farms. In fact, for the most case, that's all they're prepared to do because of the land take. And there is also quite a few that have tailwater recycle pits in some of the irrigation areas. This is infrastructure that might already be on the farm that could be made to work better and more efficiently. And I'm going back to the first discussion today about, the importance of the fine colloidal particles, not just the dissolved inorganic nitrogen as well. Capturing that fine material on farm means it can be recovered back on farm and not lost further down the system. Retrofitting into that existing infrastructure is a pretty low-cost, low-hanging fruit application. I think installing small distributed versions of perhaps that more agricultural looking one you were looking at there into the cultivated fallow land in cane and banana, which is often only exposed for short periods of time, post the final return crop, but often at a critical point in time in the climate, and I'll show that a bit later. And depending on the scale of the farming practice, and maybe more for banana, larger applications of a high efficiency sediment basin at a more sort of centralised location, perhaps at a farm discharge point, is another potential application. I've just put at the bottom there in italics that the real critical period that we see is these early wet season storms, which is October to December. And from the sugar and banana production point of view, that's at the end of their harvest period, and either when land's going into a year of fallow or where they've got new planting blocks that haven't come to stable maturity. So there's a window of kind of exposure that the catchment has to pretty extreme early storms. HES basins are not new, so there's examples that are in the ground, particularly in southeast Queensland, for quarries and landfills and construction sites. And I think the evidence base that's been built around those has helped to get the technology supported in policy and in practice, particularly in erosion and sediment control circles. Water quality performance, they're targeting the sediment and organic particulate matter from the farm paddock down to that colloidal fraction. Wetlands are doing that, relying on the framework of the plants and the biofilms on the stems and long detention times to get that coagulation process and flocculation process. This is trying to fast track it through the chemical application. Sized at 1 hour detention time, and these are event-based readings, so there's a follow-on story to this. 80 to 90% reduction in sediment, 70 to 90% reduction in phosphorus, which is obviously associated with the sediment, and the nitrogen would be particulate forms of nitrogen. Obviously, getting the fine colloidal stuff flocked out quickly is getting those results. I guess my caveat on that is once that flock is actually starting to accrete and become the sediments in the system, is in the inter-event period, how much remobilisation might you get of that held nutrient matter. And of course, if the sediments go anoxic, which they'll tend to do, then you can get release of the phosphorus in particular, and you won't get much nitrogen cycling. So I think an adaptation of what you might see as a high efficiency sediment basin on a construction site in southeast Queensland up here is what you might do to address potential release pathways. Now that's whether you plant out your primary sediment zone with macrophyte planting. So this is a kind of a mini-scaled wetland, not at 5 or 7%, but just 2%. That'll at least lock in a lot of the phosphorus. You could put floating wetland rafts in there. You could even have algal growth going in there, I guess. And, you know, that's, I guess, the innovation and the adaptations I could see. I make the point, as everyone has here today, that this is part of a system of solutions, but it's one that I see happens right at the farm and fits comfortably in what a farmer can do. Costs, well, in that small distributed scale, they can be very cheap because a farmer can build most of that, dig out a small sort of holding pond, be supplied with a very low cost dosing unit. That rainfall fed one would be the one I'd be suggesting. And for $10,000 of capex, which is, well, I won't elaborate on that, but I think it's a cost that might be borne every sort of 4 or 5 years for a farmer. And they might have 3 or 4 of these systems controlling their whole farm. So I think at any point in time, about 15 to 20% of a cane farm would be in fallow, and the rest would be in a routine situation. Bigger systems get more expensive, as you can see. Some of the establishment and maintenance issues, well, I suppose it's easy to put these things in the ground quickly, and that's important, so they can be deployed quickly and over a large area. Maintenance, sort of stuff you'd expect. I won't spend too much time on that. Replacement and renewal timeframes. These smaller distributed systems, which I'll have an example in a minute, I would be suggesting that every 4 or 5 years you just replace your high efficiency sediment basin system, which would be at the end of your 4 years of routine crops. Bigger systems longer. We've been talking about on-farm versus system scale and treatment trains. This is my take on it. A classic treatment train for farming in the reef catchments is doing the best you can, farm management, contour banks, turf into rows, all that sort of stuff. Trying to hold as much of your soil loss that you'll get as a residual through that on-farm and any nutrients that are in it for potential recovery. And then constructed wetlands, the scale, that 2% and 5 to 7% is a scale measure. I think more system repair scaled infrastructure. What might that look like? I'm just giving a quick example here. I'm thinking this kind of application is really important on the red volcanic soils in the Johnson, the more sort of erosive clay soils in the north of the Burdekin, north of the Delta, and some other regions. But a classic example is through the harvesting period, you'll end up with part of the farm going into fallow. Now, depending on how the practice is done, that can be left in a fairly disturbed state at the critical point, which is probably November, definitely up in the Johnson, when you're starting to get some pretty significant rainfall onto exposed land. And really, that exposed land needs to be managed. And if it's managed with very simple systems, it could simply be there. And I'm suggesting that might only need to function as a dosing unit for a couple of months while that land's exposed. And then the pond element can remain, because that's likely that those fallow areas will sit in a legume condition or even just a kind of a generally managed condition for a year. And then those bare paddocks that I'm showing there would go into production in the following year. The system repair stuff, if I'm putting a treatment train together, I think sits down in these strategic areas where you can basically get scaled up treatment. But the function of having these high efficiency sediment basins, which if they're planted with some wetland plants as well, can hold nutrients on farm, is that you're just taking the pressure from the catchment off those system repair projects as well. So it's putting in place a treatment train which makes sure that the wetlands and the riparian zones at the bottom there are really dealing mostly with the soluble nutrient load, and the processing of the din, which we know is a big issue. What are the strengths? Small land take, can work pretty easily within existing farm layouts, low cost, pretty low tech. They do reduce suspended sediment loads and particulate nutrients. They facilitate resource recovery on the farm, which I think is important. And it's using well understood treatment processes that have been adapted from other water treatment and erosion sediment control. So if we're talking about innovation, borrowing ideas from other places, that's, I guess, what we're trying to do here. So there are some limitations. So low pH and low alkalinity can affect the effectiveness of the coagulant, but typically those parameters would be managed actively by farmers. HES basins have not been fully implemented or are implemented at all on reef catchments, so it's not proven, so I'm not suggesting it is, but it'd be very easy to trial without a doubt. Summary, small land take, low impost on farmers, easily retrofit, simple to operate, short lead times. For that reason, it's pretty quick. If it's proven to be fairly effective, it could be scaled quickly over a large geography. Thank you.